Hello, welcome back to Basic Chemistry Plus. This is a continuation video of the states of matter, and I guess you would be able to find the last video in the description. The link would be given in the description. Today we are going to talk about the units of the universal gas constant. This is where we are going to start with, but our main focus would be on the kinetic theory of gas. The kinetic theory of gas is the one of the most important portion of the entire chapter, because if you go and see the previous year question, the graphical questions would be there. Apart from that, most of the question you would be able to see are coming from the kinetic theory of gases. From there, the RMS velocity and the different sort of velocities like the average velocity, these type of questions are very important over there. Now, today, I would try to keep this video very short. I would not solve much questions today, although a lot of questions are going to come from this particular portion, but I would try to make it short, and I would just talk about the concepts over here in this particular video. And I would make another video for only the problems over there. So if you want to understand all the things that I'm going to teach you over here in this particular video, please go and watch the previous video and then come over here. So mainly we will be talking about the kinetic theory of gases over here. But before that, we'll be going for the units of the universal gas constant. Universal gas constant is coming from our from the last video I'm saying, the ideal gas equation. I guess you do remember, according to the ideal gas equation, it was written as PV equals to nRT. Right. So the ideal gas equation can be written as PV equals to N to find out what unit of R. So R would be equals to PV by NT. So if you want to find out the unit of R, write down all the units. So pressure would be ATM, volume would be liters, and N would be number of moles, definitely, and P would be temperature in kelvins. So overall it is coming as atom dot liter dot mole inverse Kelvin inverse, right? So now the value for this particular unit is given as 0.082. Okay, this is the 0.21, you can say. This is the for this unit, but you do understand the PV is also taken as the pressure volume work, isn't it? So that's a type of mechanical work, pressure volume work. So considering that the unit of work is given in joules or in calories, so we will be having two more values of R with respect to joules and calories. For joules, it is 8.314 joule Kelvin inverse mole inverse, and if I want to turn it to calories, it is taken as 2, but properly it is a 1.98, but you can take it as 2 as well. Calorie, Kelvin inverse, mole inverse. Now you can anytime convert joules to calories, right? You know the conversion factor is 4.2, right? You can do that. And if you just look into it, 8.314 and 0.082 is also very near. The values are very near. It's like conversion factor would be near about 100, right? So it's not difficult to remember all these units. But yeah, this 0.082 would be the most important unit for you, because ATM and liter, these are the standard units for pressure and volume that we take. So 0.0821 is going to be a very important unit for you. You're going to see this unit over and over again for most of the questions. Now let's solve this one graphical questions over here. So this is a previous year question from NEET 2017. Okay. So there are 4 curves given over here. You need to find out which curve is going to satisfy the ideal gas equation. Now, if you just look into it, all the curves are drawn with respect to volume and temperature. Temperature in Kelvin scale. So in all the cases, the x-axis is temperature. And they have given some initial and the final states, like initial volume is 22.4 liter, 273 Kelvin, and the final states are 36.8 and 373 Kelvin. So they're just talking about volume and temperature in Kelvin scale. So this is definitely a question of Charles' law. According to Charles, the V1 by T1 equals to V2 by T2, we can write it. So what you have to do is, for all the states, you need to find out the V1 by T1. So like the volume by temperature equation, and it should be equals to the volume by temperature for the next state. So what you need to find out is V is 22.4 liter divided by 273. 22.4 liter divided by 273. The value which is going to come from here, it should be exactly same as 36.8 by 373. If it is the same, then this is going to satisfy the curve. And if you do this question on your own, okay, then you'll be able to see option C is the correct answer. Okay, so try to solve it on your own and let me know in the comment section if you have been able to do it. So it is from NEET 2017, as I told you. Okay, now, so this is the working formula. Got it? Now, let's move on to the relation between density and molar mass. This is also sometimes they ask you questions from kinetic theory of gases related to these type of questions. So it's very simple. PV equals to nRT. Just write it down first. Now you know when we are talking about density, density equals to mass by volume, mass over volume. So V can be written as mass by density, m by d. Now you just have to convert. You just have to write that thing in place of v. So b equals to m by d. So nRT. Now you just find out what is d. So d would be equals to Pm by nR, and that's it. Okay, very simple. In this way, you can solve the questions related to density. Now it's time we move on to the next topic, which is kinetic theory of gas. I guess you'd be able to solve the d equals to Pm by nRT related questions from now onwards, and definitely we'll be solving a few questions in the next video. So right now we'll be moving on to the kinetic theory of the gases. Okay. Now, the kinetic theory of the gases, it's talking about how the gases behave. So the gases have this high kinetic energy. So definitely you do understand they would be having some outcomes, some results of those particular kinetic energies, those translational, rotational, and vibrational motions. This is what we are going to discuss in this particular portion. The first point is all the gases are made up of very large number of minute particles. This is something we do know, right? Move on to the second. Have negligible volume and volume of the container with respect to, which means they're very small. If I just draw a container over there, with respect to the container, it would be very small, right? The particles. So you can neglect their volumes. Now, the third point over here says the molecules are in a random motion in all the directions. This is known as Brownian motion. I guess you do remember Brownian motion from class 9th, I guess. They are having some zigzag motion. They are moving into all the directions. Okay. Now, the fourth is molecular motions are completely elastic. Elastic means the type of collision where the total elastic means the type of collision where the total momentum is same, conserved. There is another type of collision which is I'm writing over here, which is inelastic collision. There are two types of collision actually, elastic and inelastic. When we talk about elastic collision, the total momentum is conserved over there, and in inelastic collision, that is not what's happening. So if I draw a car over here, let's say that we see in everyday life, let's say a car is, it's just hitting another car face to face. Okay, this is one car, that's the other car. So if they're hitting them each other face to face, then what would happen? The speed would drop, right? Let's say it is coming with the speed of 45 kilometers per hour. After the hit, they would definitely stop, or they would get deflected. The speed would decrease, or something like that would happen. The momentum would get changed. But that's not going to happen in the elastic collision. So in the elastic collision, it's like the pushback cars. Once you hit the wall, it just turns around and goes in the opposite direction, just like that. Okay. So the gaseous particle won't lose any of their momentum or kinetic energy during these type of Brownian motions. And when they're showing this motion, actually they are hitting each other. Okay, and there is something called mean free path, which is the path they are covering between two collisions. And this is something we are going to talk about later. Right now, we'll be moving on to the next point, which is point number 5. There are no forces of interaction between the molecules at ordinary temperature, which means they are not attracting each other, they are not repelling each other, no such forces are working, which is a bit disturbing for us. And you do understand that's going to get collapsed in near future, because two celestial bodies would definitely attract each other, isn't it? So that's not happening in this point, which is a bit shaky of concept, right? Now anyways, we'll be moving on to the next point, which is the pressure exerted by the gases are due to the collisions of the molecules on the wall of the container per unit area. Now let me tell you something. Let's say there is a container and you are putting some gases over there. So the gases are moving with random motions, right, in all the directions. let's say that I'm just giving it a name A. So they are moving and they're hitting the wall and they're making some elastic collision over there. So let's say this is the roof of the wall and they are hitting over there and coming back. And when they are hitting over there, they are putting some sort of forces on the wall of the container. Now this force per unit area, this is what known as the pressure, isn't it? So that's called the gaseous pressure. Now this pressure has a unit which is Newton per meter square, force is Newton and area is meter square. So putting it on SI unit, Newton per meter square is the pressure of the gases over there. Okay. Now the next point goes like the average kinetic energy is proportional to the Kelvin temperature, which means whether the gas would move with highest velocity or lower velocity, that completely depends on the Kelvin temperature. Okay. To be precise, kinetic energy is dependent and proportional to root T. Not only T, it is root over of T. This is something we are going to prove. Okay, we'll be moving into the different types of velocities. There I'll be proving that. How is it related to root over T, not only T. Okay. So any which ways, let's move on to the next topic, which is the kinetic gas equation. Okay. Now the kinetic gas equation is over here. We are proving what would be the um, total kinetic energy of a gas. So on the basis of like whatever we have done, that's the postulates. Okay, and we have quantified. If we just that's a qualitative analysis, and now if you just go to the quantitative analysis, PV equals to 1/3 mn u square on the basis of the postulates of kinetic energy, kinetic molecular theory. So on that, the quantitative molecular theory we have just learned. So on that, we are making an equation. We are deriving an equation from the kinetic theory that we have just learned. And from there, we are getting PV equals to 1/3 mn square. And you don't need to know the proof. You don't need to know the proof. But U is the velocity. Okay. Now, so this is coming from the kinetic equation. We know it. N is the number of molecules, that's Avogadro number, and M is the mass of the particle, and U, I told you, that's the velocity of the gas, right? And that's U square over here, 1/3 mn U square. Now, average kinetic energy is using the above relation. The above average kinetic energy can be found as EK equals to 1/2 mn U square. So this is also a calculation which is done in the back end, and we are getting the outcome. We just have to know the outcome. From that equation only we are getting this. Kinetic energy is equals to 1/2 mn U square. Okay, these two equations you have to remember for the time. You don't have the proof. Okay, these two equations, I guess that would be proven in your physics chapters. Okay, now what we are going to do is we are going to write this kinetic energy equation with respect to the previous equation, PV equals to 1/3 mn square. Okay, we are just going to merge these two equations and we are going to find out the average kinetic energy of a gaseous molecule. Okay, so let's just do that. Now EK is equals to 1/2 mn U square, right? Now, if you want to write this equation in terms of PV equals to 1/3 mn U square, see what I'm going to do is I'm going to write 2/3 into 1/3 into m n. Just a second. Okay, wait, not 2/3 into 1/3. It would be 3/2 into 1/3, isn't it? 3/2 into 1/3. So in that way, what would happen is this 3 would cancel out each other, right? So it would be 1/2 mn U square. So the 1/2 mn U square can be written as 3/2 into 1/3 mn U square. Now 1/3 mn U square means PV. So EK, now EK can be written as, let me check one more time. Yeah, 1/3 mn square is equals to PV now. So we can write it now from this equation. EK is equals to 3/2 PV. Now from the ideal gas equation, we know that PV equals to RT. So PV equals to RT, the EK for one more. So that's our final kinetic energy equations. This is the kinetic energy equation you need to remember. Solve questions from here. Now, this is something we are doing for one mole, right? Let's say we want to find out the kinetic energy for one molecule. Okay, if that was nmos, then it would have been 3 by 2 nRT. For one molecules to Avogadro number of molecules, 6.02 10 to by 23. Now, for one molecule, it would be R by Avogadro number Na for one molecule. Now, R by Na can be written as Kb, Boltzmann constant. This R by Na is taken as another constant, which is Kb, equals to Boltzmann constant. Okay, this Boltzmann constant value you can anytime calculate it, putting the value of R and the Na. Okay, so I guess all the things that I have taught you in this particular video, I think all of them are clear. I won't be starting the Maxwell-Boltzmann distribution curve right now in this video. I'll be making another video for that. And after that, we'd be making another video for solutions of all these questions, or the previous year questions. Okay. This Maxwell-Boltzmann theory, this is a very important portion as well. Over here, you'll be able to see there is a few graphs and like all the velocities I was talking about. All those velocities are taken care of in this particular portion, and how the molecule reacts, what is the activation energy, and all these things have been covered in this particular in the next video. So do watch the next video, and definitely subscribe to my channel. I guess that would be it for this particular class, and do watch the next video, and press on the bell icon so that you get the notification whenever I upload it.